This video explains the pigeonhole principle. So let's start with an example using pigeons. If you have 5 pigeons, but only 4 pigeonholes houses, you could place 4 pigeons in each of the 4 holes, so 1 in each hole, but there'd be 1 pigeon left over. So that pigeon would have to share a hole with another pigeon. Put that into maths. If n plus 1 or more pigeons or objects are placed into n holes, then some hole contains at least 2 pigeons or objects. Now remember, it says at least. So if we were looking at these 5 pigeons, yes, we could have 1 in each hole with 1 hole having 2 pigeons, or those pigeons might be great friends and all 5 go into 1 hole. Okay, so you're looking at least 2 pigeons or objects in 1 hole. So let's look at some examples. If 13 friends gather for a party, show that at least 2 friends have their birthday in the same month. So again, it's at least 2 friends have their birthday in the same month. More may have their birthday in the same month, but we're just looking at least. So we've got 13 friends gather for a party. We have 12 months in a year. So we could allocate 1 friend to each month. That means 1 friend is left over. So that means 1 friend shares a month with someone else. Next example. In a group of 49 people, show that at least 5 will have their birthday in the same month. So again, 12 months in a year. 49 divided by 12 equals 4, remainder 1. That 4 means 4 people to each month. That remainder 1 means 1 person has to share with the other 4. So at least 5 people have their birthday in the same month. Frank has a large number of red, blue, green and yellow counters in his pocket. He needs 3 of the same colour to demonstrate a magic trick. Determine the least number he must take out to be certain of having 3 of the same colour. So if we think about this visually, he could start by getting 1 of each colour. He then starts selecting again, and again he might get all different colours again. So he has now got 2 of each colour. If he now selects another one, that other one will be the third of 1 of the colours. So that means we have 8 here plus 1 is 9. Thinking about that mathematically, you have 2 times by 4, 2 counters, 4 colours, plus that 1 extra. 8 plus 1, which is 9. Therefore, need 9 counters to be certain of having 3 the same. Next, show that for any 5 points chosen inside a 2 by 2 square, at least 2 of them will be no more than square root of 2 apart. This square root of 2 apart is really important. You should be thinking to yourself, how do I get a square root of 2? If I think about one of the squares, the longest distance is from corner to corner. Now, on that triangle, this is 1 unit and that is 1 unit. Using Pythag, that c squared equals a squared plus b squared. 1 plus 1, which is 2, So C is the square root of 2. That's the first thing that comes into my head in regards to seeing that square root of 2. Now let's go back to the question. Show that for any 5 points chosen inside a 2 by 2 square. So if we use the pigeonhole principle, we have 4 squares and 5 points. That means one square has to have 2 points in it. The maximum distance is the diagonal, and that equals the square root of 2 units. Therefore, at least 2 points will be no more than the square root of 2 units apart. Now let's look at the generalized pigeonhole principle. If at least m times n plus 1 or more pigeons objects are placed into n holes, then some hole contains at least m plus 1 pigeons or holes. So let's look at an example. We have 16 natural numbers written on a whiteboard. Now, natural numbers 1, 2, 3, 4, etc. Prove that at least 4 numbers will leave the same remainder when divided by 5. Now, possible remainders. If we're dividing by 5, we could have no remainder. It can be divided by 5. It's a multiple of 5. 1, 2, 3, or 4. There are possibilities. Now, if we've got 16 natural numbers, you have to place those in regards to these remainders. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and then we have our next number. So it's 3 times by 5 plus 1. One number has to have the same remainder as at least 3 others. So let's think about this in regards to our generalized pigeonhole principle. We have dividing by 5, so n equals 5. That represents the number of holes. So if you think about our pictorial representation, we have 1, 2, 3, 4, 5 holes. Now mn plus 1 has to equal 16. That's our 16 natural numbers. If n is 5, we have 5m plus 1 equals 16. 5m equals 15. M equals 3. That's our 3 others. What about pigeons in multiple holes? So 7 people sit at a round table with 10 chairs. Show that there are 3 consecutive chairs that are occupied. So let's draw our table, and we have 10 chairs. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 chairs. So let's place people. We have, so there's our 10 chairs, we have 7 people. Let's go alternate. 1, 2, 3, 4, 5. So we've sat 5 people. So 5 people can sit with a chair between them. two people left. Where can we fit those two people? 1, 2, doesn't really matter where we put them. They must sit between two others. Therefore, there must be 3 consecutive chairs occupied.